Good morning, guys. How's it going? All right, guys. Topic we're doing today. So this is our Math 31 or 31 AP course. Same way, whether you're in AP or not, guys. Like that's the same material for this topic over here. The topic's called concavity and points of inflection. Okay, so again, we're in our curve sketching unit, guys, and these are telling us two aspects of our curve that we need to be able to know: concavity and points of inflection. So looking at this graph over here, the idea that we're seeing is like that. First of all, both of these are increasing functions. As we look from the left to the right, the graphs are getting bigger, and the graph's getting bigger going here as well. So they're both increasing functions. But what we see in the first graph is that if I look at the slopes of the tangents, these are kind of sketched over here, these lines, that these guys are flatter and getting steeper. So in other words, the tangents are getting bigger. So let me say this, the slopes are getting bigger. The slopes are increasing. Whereas in this one, okay, again, it's still an increasing function, but the slopes are starting steep and they're starting to get flatter. Okay, so on the second one, the slopes are decreasing. Okay, so what is true for both these ones? For both functions over here, the first derivative is positive for both. And if you remember, guys, what the first derivative tells us is that the function is increasing. Okay. Now in this one, though, we're saying that the slopes are getting bigger. So the slopes are increasing. Well, how do you measure the rate of increase of a slope? Well, if the derivative measures the slope of the tangent, whether those derivatives are increasing or decreasing is going to be measured by the second derivative. So in this case, our second derivative is greater than 0. But in this case, since the slopes are getting smaller, they're decreasing. The second derivative is negative for this one over here. Okay, so that's what's kind of different between these two curves. So the notes we have over here, this type of curve is going to be called concave up. Okay, so if concave up means second derivative is greater than 0, and then concave down for this one here means that our second derivative is negative. Okay, so and the way I like to consider this, if you think of just like y equals x squared, well, y prime would be 2x and y double prime would equal 2. In other words, the second derivative is always positive. Okay, I classify this as a kind of a classic concave up curve over here, whereas this function y equals negative x squared, y prime equals negative 2x, and that means the second derivative is negative 2. So the second derivative is negative 2. We have like what we call a concave down curve, and y equals negative x squared is going to be the classic concave down curve that I like to refer to. Okay, so guys, I can take a second here and please just read through all these notes. So guys, this is a summary of what we just discussed on the previous slide. Okay, example 16, determine the intervals of concave up and the intervals of concave down. Sometimes we call this the intervals of concavity for the function f of x equals x cubed. So first of all, we're going to figure our first derivative is 3x squared, and then our second derivative is going to be 6x. Okay, so I'm just taking the 2 comes down times 3 is 6. Second derivative is 6x. So when we look at, and I want to put the second derivative on a number line here. At this point 0, this is the 0 to the second derivative. If x is less than 0, 6x is negative. And if x is greater than 0, 6x is positive. Okay. So the trick over here is that we need to know that, first of all, this function is always increasing. Because if I look at my first derivative, so this is f prime of x. So this was a number line here for our second derivative. Here's a number line for our first derivative. Well, the 0 to the first derivative is also 0. This is what we call the critical value. So quick small thing, guys. We call this number a critical value for the first derivative. But the value that makes the second derivative 0 is not called a critical value. Okay, this is a very specific type of definition, guys, and I know that you guys will be tested on that as well. Critical values are things that make the first derivative 0. Now we look in this one. If we have 3x squared, this is positive and positive. Okay, and as you can see in the curve y equals x cubed, the function is always increasing. Well, except here where the slope is 0, the slope of the tangent is 0, but it's increasing here and then decreasing. Okay, so what we also know is that when x is less than 0, we're concave down in this part. Now, concave down is like y equals negative x squared, but the increasing part's only from here to here. Okay, so that's kind of matching up with this part from here to here. So this part here is matching up with this type of curve like that. For the concave up part, we have a parabola opening upwards, and the increasing part is from here to here. Well, that means this part is matching up with this type of curve like this. Okay. All right. So this is how we kind of sketch the curve y equals x cubed. It's concave down and increasing on this part, but then it's concave up and increasing on this part over here. This note here, the point 0, 0 is where the graph changes from concave down to concave up. We call these points of inflection. Okay, so if you look at our second derivative here, at this point, it changes from negative to positive on a second derivative. This is where we call our points of inflection. Guys, I'm going to take a quick pause, and I'm going to keep on going through this lesson in a moment.